Rajesh, warm welcome to the colloquium. Unfortunately, it's in virtual mode. So, for the rest of the audience, Rajesh Ganapathy is a physicist at JNC, and he's an old friend of many of us, going back many years at the IISc, where he did his PhD with Ajay Sood, and then later moved to Cornell, right, Rajesh, for his
Yes,
postdoc
yes, yes.
before returning to India to join the faculty at the Nehru Center. So essentially, Rajesh has developed, some of the most amazing sort of high precision imaging techniques that you can think of, which allows for very interesting and non-trivial micro manipulations of materials, and in particular, his work in understanding mechanical responses, in understanding sort of problems of arrest in colloidal suspensions, amorphous solids, glassy dynamics, etc., is really wonderful. And of course, no surprise that he's been sort of justly and very richly decorated with many awards, including this year the Bhatnagar Award. However, before I yield the floor, as it were, there are two things, especially for the younger students in the audience, that I, being an outsider sort of to the field, would like to emphasize is Rajesh's papers. I mean, they're always delightful to read, especially the way he sort of manages to distill the relevant from the irrelevant to construct arguments. I encourage the students here, especially who even have a passing interest in these problems, to actually go and read Rajesh's papers. They're delightful to read. And the second, and the second aspect, of course, I marvel at it, but not entirely unmixed with envy, is the clarity of Rajesh's talk. So, his talks are super. So he's one of those, who also communicates his physics very well. So Rajesh, having sort of built you up, I had handed to you, and we look forward to your talk, which will be on colloidal glasses. Thanks, Rajesh. Over to you.
Thanks so much, Samriddhi. Am I audible?
Yes, yes, absolutely. And your
Okay,
screen's visible and
excellent.
everything's working well.
Thanks, Samriddhi, for those very, very kind words. And I'd like to also thank Shubro for this invitation to deliver this month's colloquium at ICTS. It's both a delight and a honor for me. Living up to what Samriddhi said is going to be very, very hard. But I can assure you one thing, it's all going to be downhill from here, because I'm going to literally talk about crystallization. So I'm really rolling down the landscape right now. So there are two stories that I would like to tell you today. The first one is got to do with both the recent experiments from our group. And the first one is to tell you about how glasses crystallize. And the video that you're seeing here is basically colloidal particles in which we've been capturing videos of their dynamics and trying to gain insights into how something like a glass crystallizes. And the second story, if I get to that, I'm in no rush to get there, but if I do manage to get to that, is to tell you something about what happens if you take a liquid and wrap it on the surface of a sphere. So that's basically this droplet that's rotating here. And once again, we're going to be looking at the dynamics of these particles on the surface of this liquid droplet, and then ask questions about does it make a difference that now you're on a curved surface. And this curved surface is all the more because I'm giving a talk at ICTS. So even soft matter physicists tend to worry about curved space. I only wish it was fluctuating, then I could have worried about curved space time. But for now, it's just about curved space. Okay, so before I get going, there are two people, the two students who primarily led these two projects. The first one is Divya Ganapathy, whose work is on the devitrification of the glass, and the second is Navneet Singh on curved surfaces. And to the best of my knowledge, these are some of the hardest experiments that I've been part of, and it's really kudos to these two people for actually pulling it off. I have this long-standing collaboration with Professor Sood at IISc. He's involved with both of these projects. And I would like to, of course, thank the people, the funding agencies for the support that they have provided me. Okay, so the first couple of slides might be redundant, but just to get everybody on the same page. Let's say you take a typical liquid and you subject it to cooling. The fate is basically just, the outcome is going to be just two of these. The first one is, of course, the most familiar one, in which as you cross the melting temperature, you're basically going to freeze the liquid into a crystalline solid. Okay, and that's the more familiar one that we encounter. But then if you do manage to cool the liquid fast enough, what happens is that your particles are going to get slower and slower. At some point, they're going to be so slow that you don't even measure any perceptible movement in the particle dynamics. And then you would say that I've hit a glass. So, and this is basically the same plot being summarized in a different way. So I'm bypassing melting, I enter the supercooled regime, and the transition to the glass is not a phase transition in the conventional sense, simply because of the fact that depending upon your cooling history, where you hit the glass transition temperature is going to be different. Okay. Now, what's spectacular about the glass transition problem, of course, is that the number of different materials that we know that undergo this transition. For example, this is glass made of a pure metal, tantalum. And what I would like to draw your attention to is they have experimentally managed to get this cooling rate. It's 10 to the 14 Kelvin per second. Okay, so so if you can do that, you can even drive a single component metal into a glass. Polymeric glass, amber is something that you're familiar with. And the most recent addition to this sort of to this rich materials that fall and that show a glass transition are basically active glasses. So this is a movie of epithelial cell layers that show many features of glassy dynamics. And of course, the focus of my talk today are is one particular system, colloids, which also show glass transition. Okay. Now, what's spectacular about the glass transition is the fact that instead of looking at just the volume or the enthalpy, if you were to now start looking at, say, the viscosity or the relaxation time, by relaxation time, I just mean the time it takes for a particle to move its own diameter. Okay. Now, if you were to plot that quantity as a function of time, as you start cooling the liquid, what you essentially find is that in this very narrow window, okay, so there's just about 60 Kelvin, you basically are changing the property of the fluid, either the viscosity or the relaxation time, by about 14 orders of magnitude. Okay, so this is very spectacular in that sense. And what is even more spectacular is the fact that all the way from the liquid to the glassy state, if I were to look at the pair correlation function or the static structure factor, something that I can measure in an X-ray device, I basically see that I see no perceptible change, at least at the level of a 2-point correlator. Okay, not like the crystal transition where I see clear order develop as I go past melting. So, so that is to do with static structure. But then if I were to look at dynamics, then something remarkable happens. So what I'm plotting for you here, and this is a parameter that I'm going to keep coming back to in my talk, is I'm plotting this thing called the intermediate scattering function. It's something that you can measure in a dynamic light scattering apparatus. It just basically measures particle mobilities. Now, if you're at high temperatures, then you basically have diffusive dynamics, and this intermediate scattering function is basically an exponential decay. But as you start approaching the glass state, what happens is, like I showed you in the first slide, that particles are going to get increasingly caged, which means this function doesn't decay but starts showing a plateau. And once you hit the glass, of course, these particles never hop out of their cages, so it's essentially frozen. But on approaching the glassy state, if I were to look at this part of the spectrum of relaxations, I don't find that it is a single exponential anymore. I find that there are multiple contributions coming about. It's what we call as a stretched exponential process. So there are many exponentials coming into the process. And now, concurrent with that, if I were to now look at this particular plot, so this is log of viscosity versus 1 over T, and this is my Arrhenius fit, right? The clear deviation from an Arrhenius expression basically tells you that if I were to approach the glass transition, the activation barriers are not the same, but are evolving with cooling. And one way to reconcile both the stretched exponential relaxation and the changing activating barriers is to basically say that more and more particles start participating in a relaxation process. So that's essentially what people mean by saying that as I approach the glass transition, statics is boring, but dynamically I start seeing spatial cooperativity. Now, all of this was known about 2 decades ago, okay? And people had already, so there were theories like the Adam Gibbs theory, which basically took in these features into account, but nobody had ever shown in an experiment what this cooperativity looks like, okay? And that's where colloids come in, okay? And colloids, we know what they are, basically small particles in a fluid that stay suspended by Brownian motion. Numerous applications in industry. I won't even go into all of that. Now, if I were to take the simplest of the interactions, which is basically just what I call as a Hart-sphere interaction. So the interaction is basically 0 beyond a critical, beyond the particle size, and it is infinite at contact. Okay. Now, it turns out that colloids are the closest mimics of what you can experimentally realize in a lab of Hart-spheres. And now, because of the fact that the potential looks like so, it means that thermal energy simply doesn't matter. And the phase diagram is entirely going to be decided by just the number of particles I'm able to pack in a given volume. Okay, so and that parameter is called as the volume fraction, which is just the number of the volume occupied by the particles by the volume occupied by the container. And if I now start packing more and more particles, this is this beautiful paper that basically kickstarted whatever that we guys are doing, and what many of us are doing is this beautiful Nature paper from 1988, in which they said that if I start putting in more and more particles at some below 49% of volume fraction, I am in the fluid state. Between 49 and 54%, I am going to have a fluid crystal coexistence. And beyond 54, I am supposed to see a single crystal, which is just a face-centered cubic crystal. But experimentally, what they found is that when I get into this regime, I basically start, you see these colors that you see here are basically colloidal crystals scattering visible light. You see the colloids are about a micron in size. So the relevant X-ray wavelength would be visible light for these particles. So they're just scattering visible light, just the Bragg diffraction that's coming out of colloidal crystals. But then you will see that as I increase the volume fraction, I don't say crystalline, but I once again become this homogeneous looking suspension that I have, which is just looking like the fluid. And this is essentially the glassy state. So if I take Hart-spheres and keep packing more and more of them, I basically at about 58%, I start ending up with a glass transition. I have a glass transition. But the nice thing about colloids, as is captured by this movie, is that I can see what's going on, right? And because if I take a colloid of about a micron in size, the relaxation time, you can evaluate it. Here, A is the particle size, D is the diffusivity, and it turns out to be between about a millisecond or a second, depending on the viscosity of the fluid, which means that if I have a colloidal suspension, I can see what's going on. I can also follow dynamics as a function of time. And colloids are great because I get to control the size, uniformity, interaction, shape, all of that. Now, coming back to the problem of looking at these heterogeneities that were hypothesized but were never seen. So what an experimental group from Harvard did is to basically take a microscope and look into the dynamics of what's going on in the sample, okay? And what they found was something that people had been saying for a long time, but it's always nice to see it in an experiment. So what I'm plotting for you here is that this is experimental data that's just being rendered using colors. So what I'm plotting for you here are the top 10% most mobile particles. So I'm going to take my fluid, I'm going to identify all particles in the fluid which were very mobile. And I'm doing this for a density 5, which is below the glass transition temperature. And what you see is that as I start, so what you see in the dynamics is basically that particles that move quite a bit are spatially clustered, okay? And these are the dynamical heterogeneities that people had been talking about. Now, in a Hart-sphere system, increasing volume fraction is equivalent to cooling temperature. So I'm going to go from phi equal to 0.6 to phi equal to 0.60, which is now past the glass transition. And now you will see in this video that I don't see the sort of large cooperativity that I see here, okay? Because I'm looking at the top 10% of the given system, there'll always be some particles that are mobile, but I see that they are not as large clusters. Now, the take home from this particular movie is all I want to convince you is that even in a glass, although I don't see relaxation, it is not a quiet system. There are hops going on. I won't call them hops. There are rattling events going on, and they seem to have some small correlation length associated with the size of these clusters. Okay. Now, the thing about the glass is that once I hit the glass, of course, I am always metastable with respect to the crystal, because that's the state with the lowest free energy. So which means the glass is constantly trying to get into the crystalline state, and this process is called as devitrification.
Rajesh, sorry.
Okay. Yes.
Sorry, can I ask a quick question?
Please, please.
So for this dynamical heterogeneity, when you're talking about the top 10% particles,
yes,
in time, the particles which are in the top 10% do change, right?
Yeah. If I were to go back to this movie, you will see that this cluster stays for a certain amount of time and then vanishes. So it is heterogeneous in both space and in time. Am I answering your question? Yeah. So which is why whatever length scale I pull out of this is a dynamic length scale, right? The next instant in time is not going to be there.
Just wanted to clarify, are all the hard sphere particles of the same size? Like they're all...
Okay, so it's a very good question. The thing is, to get into the glassy state, you see, if you are taken monodispersed particles, there would be a very high propensity to form a crystal. So this is a system of bidispersed spheres. But people have also done very dense hard sphere systems in which you form a crystal, you stir it up and get into a glass. So both the experiments show similar dynamics.
So the bidispersed one is more likely to form a glass compared to...
Yeah. Because you've turned on frustration, you are you're very likely to end up in a glassy state.
Yeah. Thanks.
Yeah. So what I was telling you is that the glass is metastable, which means there is always a drive to form a crystal. And this is something that occurs in a natural setting. For example, this is obsidian, which is volcanic rock. And those white patches that you see are crystals that are formed over geological timescales. This is opal glass, which is once again devitrified. So the white spots again are crystallites. Roman era glassware. So these are things that people have unearthed and have found that actually the kind of spots that you see in them are basically crystalline artwork. And just to point out that people were worrying about devitrification. So this is a book that's publicly available. So one can actually see that devitrification was something that people worried about even before they knew atoms existed. Okay. So why is devitrification fascinating? The devitrification is fascinating because the fact that in the pharmaceutical industry, people want to make their drugs remain amorphous, because amorphous drugs dissolve about 10 to 1,000 times more easier than crystalline ones. So you want to maintain the glassy state of the drug. For example, when you do cryopreservation and you try to thaw the sample back into ambient temperature, the biggest hurdle right now is to avoid crystallization, because when you turn on crystallization, you produce these sort of sharp spikes. The crystal grows in sharp facets and spikes, which tends to ruin the sample. And people also worry about in the astrophysical context. Okay. Now, what's fascinating compared to conventional crystallization, what's fascinating about devitrification is essentially the following. Okay, and this is something that I'm sure all of you know, but I'll just tell you what's fascinating about a glass turning into a crystal. Now, in the conventional process of crystallization, the way we understand it is that you have, so when you have to form a crystal nucleus, you're going to have a penalty that you're going to pay for creating a new surface, although the volume term is going to compensate. So the competition between the R squared that comes from the surface and the R cubed that comes from the volume is essentially going to give rise to a maximum in your free energy, right? And once you cross this barrier, you're basically essentially going to form a crystal, and the surface tension is going to ensure that you try to form a compact crystal. Okay, that's when it is you pay the least penalty, right? Now you can do some trivial algebra and find out what is the size of this critical nucleus, and that turns out to be a parameter that depends both on the surface tension and this delta mu. The delta mu is basically the difference in chemical potential between the parent phase and the product phase, and this thing is delta mu here. And you can also find out what the delta G star is, which is the height of this barrier that you have to cross. Now you know from your experience by putting a liquid in your refrigerator that cooler the freezer, the faster that you tend to get an ice crystal to form, right? But that is not always the case. The reason is the nucleation time. So the time it takes to form the first nucleus basically goes as so, all right? And now this delta G star has this delta mu in the denominator. And what it means is that as you start cooling the sample more and more, although the thermodynamic driving force is becoming larger and larger, you're also providing less and less energy in terms of kBt to cross the barrier, okay? And on top of that, you also have this prefactor tau naught, which is basically some constant, which I won't go into, divided by the diffusivity of the particle in a dilute liquid, right? So this tau n is essentially going to be a non-monotonic function of temperature. So this is the melting temperature. So there is an optimal temperature at which you get crystallization the soonest, all right? And but the fact that it is non-monotonic means that if I do quench the system more and more, I am going to make it harder and harder for it to crystallize, which is why the devitrification that people have basically unearthed has never been observed in situ, okay? And it's because it's a very, very slow process. Both of these are like a double whammy that prevent a glass from crystallizing. And of course, there are no experiments in which you can basically observe dynamics over such a long time scale. So that's precisely what we want to try and achieve by doing a colloid analog of this experiment, okay? Now, the experiment itself is going to be, hard spheres, because of the very steep repulsive interaction, means that rearrangements are very, very difficult to make. So what I'm going to do is I'm going to take my colloidal system and I'm going to make the potential a little so soft so that I can speed up rearrangements in the system. All right. And I am also guided by this sort of by this study, which said that if I were to do that, the physics should not change all that much. Okay. So now once I have, so I'm going to work with soft spheres, and the soft spheres that I'm going to work with are called we call PNEPAM particles. That's some details of the particle. They have a very small polydispersity, so they have a high propensity to crystallize. So now I'm going to take these particles, put them in a chamber. Now, to prevent crystallization from the walls of the chamber, I'm going to make them amorphous by coating a few layers of particles. And then what I'm going to do is I'm going to basically take my confocal microscope and I'm going to scan it up and down. Okay, so I'm going to track every particle in my field of view. And in our experiments, we typically have about 10,000 particles in a 2D slice. That is just the region that we focus and image. And we have about 60,000 particles in the 3D volume that we scan. Okay, and now the relaxation time, so you can trivially evaluate it. So in a Newtonian liquid, the relaxation time is about 0.2 seconds. And now we are going to follow particle dynamics as it attempts to crystallize. So we're going to have this glassy sample as it attempts to crystallize. We're going to follow dynamics from about 10 to the 5 tau b, which is 1.5 days, to 10 to the 6 tau b, 5 into 10 to the 6 tau b, which is 15 days. Okay, so this experiment throws at us about terabytes of data, and we have to really sift through it to see what's going on. And just some detail that because my particles are soft now, the glass transition at which the volume fraction at which they become glassy is greater than the hard sphere volume fraction, and we find it to be about close to 0.74. Okay, so first, to convince you that I do have a glassy state, I am plotting for you the mean square displacement scaled by the particle diameter, and I'm also plotting for you the intermediate scattering function, okay, which is shown here. And as you will see that both of them are just completely flat. Okay, and this dashed line here is basically 0.14 times sigma, which is the kth size, the volume available for a particle to rattle. And you will see that over 10 to the 5 tau b, or 10 to the 6 tau b, I never see particles moving at all. Forget their particle diameter. They don't even move 1/10 of their particle diameter. Okay. But then what happens is I do have this glassy sample, but then when I go follow it in time, I actually see that the sample is crystallized. Okay. Now,
Rajesh, just a question. So these are room temperature experiments?
Yeah, these are colloids, Shubhro. So what I'm controlling really is once I freeze the system into say 0.74 volume fraction, I'm just going to watch it as a function of time, and these are done at room temperature.
Okay, okay. And there is no substantial temperature dependence, like if you heat it to like boiling point or something, these results do not change substantially.
So these being a colloidal suspension, the only parameter that we have to worry about is how much particles we can pack in a given volume. Of course, these are in water, so you don't get to play around with temperature more than a given, but we are at room temperature.
Okay, okay.
Thanks. Yeah. So, like I said, this sample is completely frozen on the particle scale, but has essentially crystallized. Okay. Now I can plot for you the crystallinity, which is just the fraction of particles in my imaged volume as a function of time. And you will see that, let's focus on the sample, which is from a 3D experiment at 4.74. And you will see that there is a long period in which nothing happens. And suddenly crystallization seems to set in, and you see this sudden jump in crystallinity. And the way we define a crystalline particle is basically a detail. So we can go to each particle, track its local neighborhood, and calculate whether it is what sort of a crystal it is. Either it's an HCP, FCC. All of that we can do by looking at bond order parameters. And all the purple particles that you see here are essentially microcrystalline particles, and you see that they are increasing. The first observation, of course, is the fact that, like crystallization from a liquid, these crystals are not compact. Okay, because in the liquid, the surface tension term would have made it a very compact crystal, but that's not what I see. That's not what we see in our glass samples. Okay. Now, I have already told you that unlike a liquid, a glass is also not homogeneous. So the question that we can ask is, I see many crystallites in my sample. Do they all crystallize in the same manner? Okay, so I'm going to show you two movies now. Okay, and these are movies that I stare at even when I'm not giving a talk. I am a big fan of these movies. So let me first tell you what the color codes are. If you see something red, it means the particle is not moving at all. And if you see anything other than red, as you go up the color scale, it means the particle is moving more and more. Okay, and please note the cutoff is only 0.6. Okay, which means a particle doesn't even get to move its own diameter. Just about its own diameter. Okay. This movie is also over 3 days, and I'm speeding it up for you by a factor of 11,000 so that you can observe it now. All right. Now let's see what happens. So this is a 3-day movie, and what you will see are that there are these sort of displacements in which no single particle makes a large move, but there are a collection of particles which make these short moves, and at the end of the day, you have this nice, beautiful crystalline patch, okay, which is just visible. All right. And now I can plot the x of t for this particle. And the first thing that you see is crystal growth, like I said, is by local particle shuffles. There is no macroscopic diffusion of any particle, which is forbidden because I'm in a glass. And the key thing to note about this profile is that you see, if I had a crystallization happening from a liquid, because I have to cross an activation barrier, there would be a certain time for me to do that. And it would take, so there's sometimes, it's called a nucleation time. Except in a glass, what I see is that the minute I do the quench, I start seeing this increase in crystallinity. Okay, so the x of t that I had shown you earlier was over an average of all crystallites, but if we were to dissect what each individual crystallite is doing, one growth process is via this. But then something that's even more spectacular, so the movie is basically the same, the color codes are same, but I'm now looking at a different crystallite, and I hope I can catch the event for you precisely. You see the sudden increase in activity, and the minute there was this sudden increase in activity, you basically had a crystal emerge. Okay, so in this movie, what you're seeing is not particles moving, not a small number of particles moving, but you see a large collection of particles moving. And so you're going to see it again in a little bit. This one here. Okay, that streak of activity that you saw. Okay, so for this crystallite, if I were to track what's going on as a function of time, what I see is not what I saw earlier. I basically see an increase in crystallinity, a long plateau in which nothing changes, then there is an abrupt increase in crystallinity followed by a plateau again. So This process is very different from what I showed you earlier. And this sudden burst in activity is what I'm going to call as an avalanche. And avalanches involve many tens of particles, and also particles that participated in an avalanche are not the ones that crystallize. So basically, I see the spurt of activity and crystallization gets triggered in neighboring regions. Okay. Now, before we started these experiments, of course, we were guided by some simulation studies, and we want to just map on, we'll try to map on what we see with what's known in simulations. So there were two sets of simulations done, and let me first show you the first one. So this was the work that came out about 10 years ago. And what I'm once again plotting for you is x of t as a function of time. And if you have a supercooled liquid, okay, of course you get compact crystals because you are at a low enough volume fraction. But if you are in the glass, what you do see are that that the x of t profile that they see is basically increases steadily. Okay, this was for a poorly annealed glass, and what you also see is the crystal shapes are not compact. So I am showing you this for a volume fraction of 0.61 in the simulations. Okay, and just like what we saw in the first route, there are these small clusters of activity and they trigger crystallization nearby. Okay, so that's what they have found. Now they also did another bunch of simulations in which what they did is they had a whole bunch of ensembles of these glass samples in the simulation box, and every sample that had a tendency to crystallize soon, they removed it from the simulation. So they only looked at glasses that crystallized after a very long time, and they called it well annealed glasses. And what they see, you see, this is once again for phi equal to 0.61, which is precisely what they did earlier for a poorly annealed glass. But now what you see is if you were to plot x of t as a function of time, you essentially see this nice steps, just like the one that we saw. All right, and this is once again a movie. I'm not going to play it here, but this essentially says the same thing. Okay, so in simulations, you have to follow two different protocols to see the two different routes of crystallization, whereas in our experiments, you have a single glass sample and we were observing both the pathways. Okay, and now what you can do is from this sort of crystallinity profile, you can basically find out by fitting a line and looking at deviation from a straight line, you can quantify it as either an avalanche mediated growth process or a smooth growth process. And we had about 12 crystallites grow in our sample over the 3 to 4 days over which we tracked the dynamics, and we found that about 6 of them went through a smooth growth process and about 6 of them went through an avalanche growth process. Okay, so experimental glass samples show features of both simulated poorly and well annealed glasses. Okay, and the question of course is, we have just taken the sample, mixed it and thrown it into the container and started imaging. The question is of course, why do we see both the pathways in our experiment? Okay, now you can do a very simple analysis. So to understand if so we know where the crystallites grew, so which means that we can look at the very initial time series of our images. That is when there are no crystals at all in these images in the field of view. And what we can do is we can plot the pair correlation function. Okay, and this is for an avalanche process. So there's the red one here, and that's for a smooth growth process. So I'm looking at regions before crystallization happened, and I'm calculating how are they locally arranged. Okay, and the fact that I have a taller peak, because of the fact that if I were to integrate the area under the curve, what I'm going to get is the number of particles in my nearest neighbor shell. The fact that I have a taller peak means that regions where an avalanche process went through means that the particles are better packed. Okay, so in experimental laboratory prepared glass sample, because I've not done any special procedure to either create a poorly annealed glass or a well annealed glass, I am essentially going to see regions of density inhomogeneities, and these density inhomogeneities are going to give me two different routes. Okay, so this is where we were about 2 years ago, and these are the first experiments in which we have been able to visualize glass samples. So we are very proud, and we go to this meeting called the Unifying Concepts in Glass Physics, which was held in Bristol, and we drag this theory and computation legend to the poster. And we show him everything, and he says, "Oh, this is all very nice, but tell me something I don't know." Okay, and you can imagine the sort of blow that it was. You see, what I actually wanted to say was, well, professor, now you know the simulations are correct. But then I never had the audacity to say that. But this comment really got us thinking about how do you now say more than what is already known in the simulation, okay? And roughly about this time, there were a bunch of studies that were coming about in which people were using machine learning techniques to actually predict dynamics in glasses, okay? And I won't have time to go through at least the more recent one. If you're interested, you should really see this, the Google DeepMind paper, which made waves a couple of months ago. Now, the question is, can I now use machine learning and use some sort of a structural metric to understand why a glass crystallizes and how it crystallizes? Now, and before we ask this question, there were also some hint from simulations which basically said that there is some link between Devitrification and structure. So you could look at the local bond order of the particles, and there were some links that people were trying to already say, but nothing was very conclusive. So what we're going to do is the simplest form of machine learning, which is called as supervised machine learning. And let us say that you essentially want to classify, so you have a whole bunch of images and you want to classify them as being cats or dogs, okay? So those are the classifiers, cats and dogs. And now for each of these images, you're going to need a bunch of descriptors, okay? Now, the idea is once I have the best descriptors for my system, and if I'm able to plot it like so, can I find a plane that separates out cats and dogs? So every time I now throw a new image into my system, it's either going to be C1 or C2. Okay, so that's essentially the idea of machine learning. The idea is to classify them and then find this dividing plane that best separates out the data. All right. Now, in the context of glasses, we know what the cats and dogs are. These are particles that move, and these are particles that don't move. Okay, so what we're essentially going to do is basically look at the trajectories of these particles. So this is, for example, a trajectory of a particle that made a hop at a particular time. Okay, so it was quiescent for some amount of time. Suddenly, at some time, it made a hop, and then it stayed quiescent again. Okay, so these are particles that have a tendency to hop. And now what we're going to define is we're going to define a function called as the p-hop function, which basically looks at, which don't worry too much about the definition here. All it does is it goes looking at a trajectory like this, and every time there's a hopping event, a genuine hopping event based on a cutoff, we basically see a peak in p-hop. Okay. Now I'm going to call soft particles. So these are like my dogs, which have a tendency to hop, and my hard particles, which are lazy and don't hop, are my cats, and they have a tendency to not hop. Okay, and now what I'm going to do is from my experimental data, in which I have all the particle coordinates as a function of time, I'm going to find out 600 particles which made hops and 600 particles which didn't make hops over a certain amount of time. All right. Now, once I find these particles, I am going to identify them, of course, and then I'm going to see what is their local neighborhood like. Okay, so I'm going to define, so these are my descriptors. My descriptors right now are basically how is the density around this particle that I'm calling a soft or a hard particle. Okay, and we're going to use a function like this, and this function gives us, for the parameters that I've used, it is going to give me 47 descriptors of how density is locally arranged around this central particle. Okay, and I'm going to call this descriptor my structure functions. All right, once I have my structure functions, I'm going to have each of these structure functions as the component of a vector in an m-dimensional hyperspace. And then I'm going to try and find out in this m-dimensional hyperspace whether I can find a plane that separates my soft particles and my hard particles. Okay. Now, please note that if structure is not related to dynamics, then your descriptors are complete junk, which means that you will not be able to find a plane that separates soft and hard. Okay, but if you do find a plane, it means there is a correlation between structure and dynamics. Okay, and once we have the training set, we are going to now look at all particles in the field of view. We are not going to look at how they hopped. We are not going to do anything. We are only going to look at their local structure. Okay, and see if you are able to classify. And what these machine learning papers essentially showed is that you are indeed able to classify particles based entirely on the structure, and you're able to do it with 77% accuracy. Okay, I'm going to take this analysis now, and I'm going to put it on our machine and put it on our Devitrification data. And essentially, I'm going to go to each particle, looking at its hop, classify it as soft and hard, then do the structure function analysis and classify every particle as being soft and hard. Okay, and I'm going to do this machine learning analysis only over the initial 10 to the 4 seconds of the experiment, where I did not see any crystals grow. Okay, so this is the time over which my sample still stays amorphous. Okay, and I'm going to go one step above the simulations. I am not just going to look at soft particles, I'm also going to look at soft particle clusters. Okay, I'm going to look at cluster sizes that are greater than 6, and we found that this worked great for us, and that's why we are doing this. I have no other justification for looking at a cluster size greater than 6. Okay, so these are my soft particle clusters. TNE is the time over which I didn't see any nucleation. These are my hard particle clusters. Okay, of course, soft and hard particles do not overlap in space because these are locally different in their local structure. But then these are the crystals that appeared much later. And you will see that crystals essentially grew in a region which I could already classify even before the crystal grew as being soft. All right. So where crystals grow in a glass as a very strong correlation with the underlying structure of the glass, and that's what these images are trying to show. Right, and we also found that softness cannot just tell you where it grows, but we also you might recall that I told you we found 2 different pathways for the devitrification process. We call them the avalanche and the smooth growth process, and if you were to correlate it with the softness and the number of times the soft particles appeared there, you find that once again you see 2 clusters. So softness not only predicts where crystals will grow, but also tells you how they are going to grow. Okay, and the studies that I mentioned to you earlier about which had alluded to the possible connection between structure and crystallization, I basically said that if you were to look at some sort of an order called as medium range crystalline order, you would see that crystals later on tend to grow in those regions in the glass. And we also did that analysis. But what we find is that the take home from this is that softness, which I'm plotting for you here, is better correlated with crystallinity, which I plot for you here, and then MRCO. And what you're seeing here, this I is basically the box index. So I'm going to go to each box, calculate the number of MRCO particles, the number of crystalline particles, and also the number of soft particles, and you see softness does a better job than MRCO. Okay. Now we can do one thing more than what we've done so far. What we can do is we can take another glass sample, which is not in which we don't analyze anything at all in the dynamics. We are just going to take the machine learning protocol that we developed earlier. We are going to look only at structure and try and see if the ideas that we had earlier can predict. And this is once again what you're seeing is that these are soft particles. These are hard particles, and you see that crystals predominantly emerge in regions with a very high softness. So the take home is basically that although the glass at the level of a 2-point correlator looks pretty boring, there is actually structure hidden in the glass. Machine learning can find it for you, and that's precisely where the crystals will grow. All right. So this is the first part of my talk, and I think I have about 5-6 minutes left. So if there are any quick questions, I can do that, or else I can go to the next
one. I was wondering if there has been any analytical studies to go beyond 2-point structural correlations to understand these.
Yes. So 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 there are. So I presume you mean 2-point static correlations.
That's what I mean. Yeah.
Yes. So there are a bunch of papers from about 10-15 years ago in which they are looking at length scales associated with the parameter called as the point to set length. So the idea of a point to set length is that so one way to realize a point to set length, which I'll show you very soon, is to have a frozen boundary and look at how does the static boundary influence dynamics or ordering inside the bulk of the glass. So there has been some attempts there, and there you find that this point to set length scale grows much more than what your 2-point correlator would have shown. Okay, but it's still, when I say much more, we are really talking about a number from 2, which is for the 2-point correlator, to a factor of 2 to about 5, which is for the point to set length. So it's still not a very large growth.
Thanks.
Yeah. Okay. So I think I really have run out of time, but I'll quickly tell you something which Navneet has been doing. The idea is to basically look at what happens to liquids on the surface of a sphere. And going back to the favorite plot of mine, so I'm plotting for you the log of viscosity versus the relaxation time as a function of 1 over temperature. Now, we basically were talking about how a glass can still crystallize, but then there is something very fascinating about this plot, okay? And the idea is that, so the basic thing is, so we know there is a theory called the mode coupling theory, which doesn't describe the slowing down. It starts deviating from the relaxation time data quite early on, okay? Now, there are these two other approaches. One is called as the random first order transition theory, which basically says the relaxation time diverges at a finite temperature T naught. That fits the data beautifully well. There's also this theory called the dynamical facilitation theory, which says the relaxation time diverges only at T equal to 0. So this is a purely kinetic theory, this is a purely thermodynamic theory. Both of these lines fit the experimental data equally well, okay? So one of the biggest challenges is, if you have theories that equally predict what's going on, then how do you tell which one is the right one? Because one is thermodynamic, one is a purely kinetic phenomenon, right? The idea is, how can colloid experiments contribute? And so a little while ago, so there was also this question on this some time ago. So one way to probe these sort of dynamical heterogeneities and also look at the correct, to get a better feeling for which would be the correct descriptor of the glass transition, is we took this glass and we froze a wall of particles. Okay, so this is a wall of particles frozen using an optical tweezer, and we basically quantified dynamical heterogeneities far away from this wall. Okay, now what we found is, as you increase the volume fraction, these dynamical heterogeneities basically go from more stringy shapes to more compact shapes, and that is a prediction that is unique to the random first order theory. So although they fit the relaxation time data equally well, only one theory captures this essential part of what the dynamical heterogeneities do, right? Now, and this theory called the random first order theory has been tested in numerous experiments on flat surfaces, okay, or in flat space, okay? And what we wanted to do, just for the heck of it, is to see what happens if you now have a curved surface. Does R of 40 still describe what's going on? Okay. Now, this is essentially some very basic thing. Let us say I have a flat surface. Now, by flat surface, I essentially mean that if I take a vertex here and I were to go around it, then if I am flat, then assuming that I am triangulated this flat sheet of paper into equilateral triangles. So each vertex here is basically subtends an angle pi by 3. Now, if I have a surface of 0 curvature and I go around this, it means 2 pi minus 6 into pi by 3, because I have 6 of those is going to be 0. Okay, but the minute I do the following, I take a cut, and now I overlap the orange and the gray regions. Now you're going to have basically this sort of a shape, and for this sort of a shape, if I were to go around in a circle, basically I'm going to now have a missing triangle now, so I'm going to pick up an angle deficit, which means whenever there is a curvature on a surface, I'm going to pick up an angle deficit. Okay. Now for a sphere, we know that the total curvature is 4 pi, which means the angle deficits have to add up to 4 pi, which means I have to have 12 pentagonal defects. Okay, and this is precisely why a soccer ball will have 12 pentagons. Colloids on a curved, colloidal crystals on a curved surface will have 12 pentagons. Your SARS-CoV-2, at least the artist's rendering of it, has 12 pentagons. Okay. Now, why do we have to care about curvature, right? So by putting these sort of pentagonal defects in a system which likes to pack into a hexagonal tiling, we are now introducing disorder. Okay. And now it turns out, so by putting on curvature, you can now induce glassiness in the system. And I won't have time to go into this, but you can also take icosahedra, which are 5-fold symmetric objects, rotationally 5-fold symmetric objects. These icosahedra will never be able to tile flat space, but you can now take icosahedra and you will be able to tile a 4D hypersphere. Okay, so curvature can both induce and promote glassiness. And all of this is captured by this theory called the frustration-based theory of the glass transition. Okay, so what we wanted to see was whether RFOT works here. So I will briefly tell you about my experimental system. The experimental system is an oil droplet into which I'm going to put in charged colloids. Now I have a oil phase and an aqueous phase, which means if I have a charged particle, your Jackson second chapter will tell you that I will have to now create an image charge, and that image charge is basically going to drag this particle to my surface. So I basically have a droplet on which I have particles freely diffusing around, but these are on a curved surface. And to avoid crystallization, I have basically taken two different sizes of these particles, and these are the dynamics that you see. And just like phi, my parameter that controls glassy dynamics is something called as gamma, which takes into account both the number density of the particles and also the fact that these are charged particles, so which means the interactions are dipolar at the interface. Okay, and this is at a denser for a denser or a higher gamma where the system is more frozen. And we can do the topological charges on the surface, and we basically see that just like you had for a crystal, you basically need 12 pentagonal defects, although the defects themselves can fluctuate. So each of these polyhedra that I have here, I'm calling it polygons that I have here, I'm calling it a defect. Hexagon is 0 charge, pentagon is +1 charge, and hexagon is -1 charge, and so on. But they all add up to 12, which is mandated by geometry. But then these defects do fluctuate. And what I can do is cut to the chase and just tell you what happens to the cooperative dynamics on the surface of a sphere. So I'm showing you, just like I showed you in my devitrification data, I'm showing you time average snapshots of particle mobilities, and you will see that particles are basically evolving in a highly cooperative manner. And now we can ask whether in this particular system, just like we found in flat space, where the dynamical heterogeneities were changing shape, do these also change shape? And so we can basically go to each mobile particle, and you will realize that if I had a string-like, dynamical heterogeneity, it means I basically have one neighbor in front of me, one neighbor ahead of me, which means my fast nearest neighbors are basically 2. But then if I had something more compact, I would see something different from 2, larger than 2. And this is for the system on the curved space. But just to tell you that the shapes of CRRs, this is in flat space and this is on a sphere. Just like in flat space, you once again see a compaction of these CRRs on a curved surface as well. Okay, so we did a bit more, but I think I've clearly run out of time now. So I'll just come to the last slide of my talk, which is to basically tell you that this predictions from the random first order theory, which have been tested on flat surfaces, works also on curved surfaces. I didn't have time to really tell you about this, but maybe at a later stage. The thing that I would like to leave you with is that colloidal suspensions are just beautiful models to study these sort of phenomena. With that, I'd like to thank you and take questions in whatever little time I have. Yeah.
Thank you so much for that wonderful talk. If there are people with questions, you can just maybe unmute your microphone and go ahead and ask the question.
Hi, this is Shashi. I have a quick question. Hi, Rajesh. Wonderful, nice, very nice talk. Hi. So maybe I missed this point, but what about the experiments allowed you to do the machine learning analysis, which simulations wouldn't? Maybe I missed this point.
So let me get to the slide. So the question is, what allowed me to do machine learning with the system?
Right, because you kind of led into that, saying that the simulation person made a comment.
So it's all got to do with the chronology, Shashi. So when people were trying to link devitrification to structure, the machine learning approach was not in place. So they were looking at structural signatures that were not captured by machine learning. They were looking at local order based on, like I said, the medium range crystalline order sort of parameters, and they did find a link. But what machine learning allows to do is to just make it, in fact, we don't even go looking for any sort of crystalline order in the system. We are basically just classifying particles as soft and hard based on their propensity to make a hop and that is being quantified entirely from structure.
Sure.
Yeah. And looking at the structure around by looking at the structure using this 47 parameters, which is essentially a density correlator. Yeah.
Right. Sure. Yeah. Thanks so much.
So Rajesh, there was a question in the chat box. I'll just read it out, and related to what you just said. Could you reiterate the role of machine learning in the prediction? Where does the crystallization occur?
Right. So let me just focus on this slide. So you see, soft particles are particles that have a propensity to make hop, and that is something that I'm trying. So I use a training set to first train my machine, but once I've trained my machine, those particles which I'm classifying as soft are ones which have a certain local configuration which allows them to make a hop. And when I look at my crystal growth, it is basically crystals grow in regions with a high softness.
Rajesh, could you elaborate a little bit about the form of that structure function? Like, what was the intuition behind that?
Oh, so right. So what I'm basically doing is it is essentially like a 2-point correlator, except that I am going to each particle now, and I'm calculating what does the density field look like at a given distance, which is set by my probe length scale mu here. All right. So instead of just so the G of R that people typically plot is averaged over the entire system over all particles. Here I'm going to each individual particle and asking what is the local organization. And this probe length scale is something that I vary from 0.4 sigma to 5 sigma. So 5 sigma being the particle diameter. So I'm going to go to various distances. Just look at how particles are arranged in a particular shell around this particle. That's all. That's all there is to the probe function, to the structure function.
I assume, I mean, in machine learning, if you want some support vector machine to work out nicely, usually you have to go to the right coordinates for the classification to work out nicely.
Correct. So precisely. So which is what I meant by saying, as long as you have the right descriptors for the dynamics, you should be able to start using machine learning. Right now, this is the stuff that we guys didn't do, but it was laid out in a numerical study by Liu and co-workers about 4 years ago, in which they said that if you were to look at these particular structure functions, which are essentially nothing but looking at densities at some particular distances, you are able to make predictions about dynamics. Now, adding on to what you're saying, adding on to what I'm saying, what you could also do is to not just look at the distances, but you could also look at orientations of how particles are arranged, and they found that that didn't matter as much. So the descriptors that they arrived at were pretty good descriptors. Yes.
I see. Interesting.
Yeah. So I see. Oh, I can also click on the chat. Okay, so fine.
Yeah. I think there was just the one question on the chat.
Okay.
Are there any other questions from the audience? No. Okay. If not, we'll all virtually thank Rajesh for this very wonderful talk. Thank you so much.
Yeah. Thanks.